Right
Okay.
again. Okay. Hey, Astronomy 151. This is Lipkin. We're going to talk today about comparative planetology. It's in chapter 6 of your book, but you don't really cover that in your topics. We cover this topic in celestial mechanics, which of course we should just about be getting done with. I wanted to talk about in this video what all the different terms and celestial mechanics means and why we wanted to be able to do them, kind of as an overview. So it starts off with Kepler's law, R is equal to P to the 2/3. Usually when an object is discovered, they're going to be able to measure how long it takes to go around the sun, and so they'll measure its period for how long it takes to orbit. Now this, of course, will tell you where it is. Okay, if it's out beyond 1.5 AUs, then it's beyond Mars's orbit, and it might be a Plutoid. If it's beyond Pluto's orbit of 40 astronomical units, it probably is a Plutoid, unless some of these other numbers tend to make us think that it's not a Plutoid. At any rate, so that's a pretty good indication of if it's a planet or a Plutoid. The next one we come to is the V orbital, and whether or not it's fast or slow. Now, of course, it's fast when the planet is near the sun, right? And of course, that's the law of universal gravitation. This planet has more force acting on it, so of course it's going to be going faster. Okay, and that's why that's important. But that's also important because in the bombardment era, a planet like Mercury would be much more likely to get in a violent encounter than a planet like Pluto would. So that's a really good indication of how fast or slow the planet's going in orbit around the sun. And it tells us some information about the planet in the past, but it also is really interesting from the standpoint of, can you imagine a star orbiting another? Okay, so where we were at, where we were talking about the orbital velocity of a planet around the sun, and where this is actually interesting is when you see a star in orbit around an unknown object, and it orbits that object in 13 days. That's got to be a really fast orbital velocity, right? And that was a star in orbit around something else. Man, that something else really has to be a big something else, right? Anyway, that might give us a clue that it was a black hole later on. Anyway, so that's why orbital velocity is important. The next one we come to with celestial mechanics is, of course, surface gravity. Now this one I like to think of as how big is the object. You know, if it's a big object, it'll have a lot of surface gravity. Now you'll notice that Jupiter's surface gravity was 2.5 times more than Earth's surface gravity. Now what might be surprising is Saturn's surface gravity was only about the same as Earth's surface gravity. But it does allow us an initial picture of how big the planet is, and then you figure out the weight of the car on the planet. Now, the weight of the car on the planet, we picked 2,000 pounds in this traveler's guide, and of course that reflects the weight of a car, just so we know. But if I can pick the car up like this, then that's not much of a planet, is it? And so that kind of leads us to one of our quick and easy things, which is all planets had at least 1/3 the surface gravity of Earth. Mercury and Mars had the smallest surface gravity of only around 3 meters per second squared. And so a car was still significant enough that I couldn't lift it up. But it was getting close, okay? But those two were planets. When you got to the weight of the car on Pluto, you'll notice that the weight of the car was not so significant that actually I would be able to lift it on Pluto. I'd be able to lift the car up, and so that's why Pluto's not much of a planet. Here, there's one other thing to point out with surface gravity and all these other terms that we've talked about so far, and that's how close Venus is to Earth by the numbers. That Venus and Earth have almost identical numbers by this celestial mechanics stuff, and that gives rise to, of course, Venus being called Earth's sister planet. Now, as you study Venus, you'll see that, in fact, Venus is a lot different than Earth is on the surface, and its atmosphere is a lot different as well. But the two planets, Venus is actually the closest planet to Earth as far as by the numbers, okay? Now, of course, closest climate to Earth would be Mars, but that's for another day. The last thing here, and this is the last thing I wanted to talk about, was escape velocity and how important escape velocity was for determining a planet and whether or not what that planet is going to be like. And the way I like to think of escape velocity is, you see how I've got my planet here and I've got this atmosphere going around it? Well, okay, great. You know, how big is the atmosphere for a planet? Well, it depends on its escape velocity. If you have an escape velocity like Earth's, then you'll have a relatively large atmosphere, like Earth or Venus have a pretty big atmosphere, don't they? If you have a small surface gravity, like Mars or Mercury, then you'll have a smaller atmosphere. And of course, for Mars and Mercury, their escape velocities are very low, and that allows their atmosphere, at least in Mercury's case, to just evaporate into space by itself. All right? And so Mercury isn't able to keep an atmosphere. It only has a tenuous atmosphere, or what they call a transitory atmosphere at best. Okay, Mars has an atmosphere like being up in our sky at 60 to 70,000 feet. That's well over Mount Everest, by the way, so that's super high in the sky. But now that we're on the subject, you'll notice that the escape velocity for all of the Jovian planets was huge. The escape velocity for Uranus and Neptune was over twice that of Earth's surface escape velocity, and for Jupiter it was over 4 times faster than Earth's escape velocity. Now what that means is, on these giant planets like Jupiter, Saturn, Uranus, Neptune, the gas giants, the reason they retain all their atmosphere, or one of the reasons, is of course because their escape velocity is so huge. It's hard for the gases to escape from those planets, unlike the moon, where the escape velocity was so small for our moon that it's unable to even keep an atmosphere, even though it's in a relatively good place in the solar system for atmospheres. And you can tell because all the planets in this area have an atmosphere, but our moon does not. At any rate, so the last little trick, and that's what I really wanted to make this video about, was to talk about how you can look at a combination of your surface gravity and your escape velocity, that when you see those two numbers, you can tell whether or not the planet is a terrestrial type planet or a gas giant like Jupiter or Saturn. At any rate, so this will give you really good information, I think, on being able to solve the is it a planet or a Plutoid, okay? Which is, if it comes out to have a orbital radius of bigger than about 3 AUs, you know you got problems. It's probably a Plutoid. However, if it's got a surface gravity that's approaching Earth, then it's a planet. If it's got more than 3 meters per second squared for a surface gravity, I would call it a planet. All right. And then last but not least, is it a planet or a giant planet? If you have a surface gravity around Earth's surface gravity and you have an escape velocity more than double Earth's escape velocity, then you're probably a giant planet, like a Jovian planet. All right. At any rate, I hope you can understand how this comparative planetology and looking at the planets by the numbers is really interesting, or can be, and that's why we, of course, are covering it in Astronomy 151. All right. Well, good luck to you on your tests, and we'll see you soon.